Okay, welcome back, everybody. We're going to get started here on step 2 of Szabo and Ostlund's algorithm from page 146. And this is the longest of the 12 steps. We're going to calculate the 1-electron integrals and the 2-electron integrals. But the good news is they only have to be done once. We don't get into the iterative part of the algorithm until step 5. So step 2 may be kind of long computationally, but when it's done, it's done. None of these values will change then for the rest of the program. So let's go ahead and get started here. Let's highlight this so we can see it. So there we go. We've got basically 4 things to do here. We'll do 3 of them are 1-electron integrals. And this is where I really like Szabo and Ostlund, and also the little textbook by Charles Quinn is actually give you these equations. They're based on the idea of taking a product of Gaussians and getting another Gaussian, then evaluating these multi-site integrals. And I found to my dismay, as I was trying to learn this on my own, relatively few references give you these equations, and without these equations you're really stuck. You can't do these computations by yourself. So it's really because of these 4 equations we're going to be using here that are found in the appendix that makes me a, a number 1 fan of Szabo-Ostlund and of Quinn. So yeah, let's get going here. Let's send this information in to Mathematica. First of all, we start off here with a number of initializations, set these sums equal to 0. And the first 4 here, the S's, are the overlap integrals. And part of the the issue here on the self-consistent field algorithm is that these basis functions are not orthogonal to each other. We will be getting non-zero off-diagonal elements, so that requires then this orthogonalizing within the iterative part of the algorithm that we'll see later. But here we'll just calculate them. So the S11 through S22, that's going to fill a 2 by 2 S matrix of overlap integrals. The T values are kinetic energy values for each of the electrons. That'll form a 2 by 2 matrix. So that'll be T11 through T22. Then we'll have a 2 by 2 matrix based on the attraction between the electrons and site A and the electrons and site B. So that'll be 2 more here, VA11 through 22 and VB11 through 22. So we start off by just setting these sums to 0. And then we begin the calculation. So this will be inside a double loop. We will be looping doubly over the number of contractions in our Gaussian basis function set, which you'll recall is 3 for STO3G. So this will be a double loop from 1 to 3, or 1 to L as we call it. So here are these wonderful equations. We'll try and derive them or discuss them in particular. The derivations are in the appendix of Szabo and Ostlund. And A.3 equation gives us the overlap integral. A.11 gives us the kinetic energy values. So we'll just plug into the values here. No fancy looping or use of symmetry here. We'll just calculate these values here. S for the overlap, T for the kinetic energy. And then they're done. That's it. We go on to the attraction potential between the electrons and the nuclei, the positive nuclei. So we'll have to do a set here for nuclei A, the helium, and nuclei B, the hydrogen. So these wonderful equations in the appendix come to our rescue, enable us to do this. So it'll be A32 and 33 here to do the electron nuclei attraction integrals. So just plugging into these equations, pretty much just typing them in the way we see them in the textbook. Here they are, the way Szabo and Ostlund use them. Not trying to be fancy here. If I wanted to be even the least bit efficient here, I'd use some kind of a subroutine and then call the subroutine with different arguments, but I didn't want to go into even that much fancy Mathematica programming, so I'm just plugging into the equations multiple number of times. So calculate the 1-1 term, the 1-2 term, the 2-1 term. It will be a symmetrical matrix, so the 2-1 term is equal to the 1-2 term. So just calculate the 3 unique values here. That'll fill up the matrix. So just repeated use of A32 and A33 here. Then we will repeat the whole thing for the hydrogen nuclei. We will come down to calculate the VBs, the VB11. Again, using the same equations here that work very, very nicely. If you're interested, the derivation for this is a little more involved, using Fourier transforms for this one and for the 2-electron integral, which I found to be quite a fascinating derivation. Appealed to me as a math teacher. But you don't have to go through the derivation to use them. In fact, when I typed these in, I hadn't derived them yet. I just typed them in, really not understanding their origins. Just typed them in out of the appendix of Szabo and Ostlund. So there we are. We went up here. We did site A. Then we do site B. Let's make sure we actually did that. And then we should get some output here we can compare with that given in the textbook. Let's make these visible. So yeah, here we go. Here's the overlap integrals. And you can see the off-diagonal elements are not 0. So these basis functions that we're using here are not orthogonal. So that's going to require an orthogonalization step and a change of basis step that comes up here later. So there it is. Here's the overlap integral. Here's the kinetic energy, or I should say the overlap matrix. Here's the kinetic energy matrix, the nuclear attraction matrix to site A, the helium, and the nuclear attraction matrix for site B, the hydrogen. So if you have the Szabo text available, he does give some intermediate values. They should agree with these values perfectly. We can then calculate the core Hamiltonian matrix, not dealing with the electron-electron interactions, by just adding these together. Kinetic energy plus the attraction to each of the nuclei. And that gives us our core Hamiltonian, which is fixed. It's done. It's fixed for the duration of the self-consistent field calculation. So with that, we're down to the 2-electron integrals. Let's bring this up. Let's make that visible. There we are. There are actually 16 2-electron integral values we need here. It'll be like 2 to the 4th power is 16, but there are only 6 unique values that we need. Once we have the 6 unique values, we can fill up the array of 16 values using these. And if you want to show that to yourself, just write these out in so-called what they call the chemist notation. Keep in mind that you can switch dummy variables 1 and 2. The 1s can become 2s, the 2s become 1s, and I believe you have to make use of the fact that these are real, not complex values we're dealing with here, and then you can show that the other 10 values can be derived from these 6. So you can go through and do that yourself if you want to convince yourself of that. But we're just going to calculate the 6 values we need here using this wonderful A.41 in the appendix of Szabo and Ostlund. Again, this was a rather slick Fourier transform derivation that yields this extremely useful equation. So there it is. We're going to calculate 6 different values here. Let's kind of go through this. Again, it'd be efficient to do this with some kind of a subroutine, but I just calculated the values we needed and then plugged into the equation. I'm using Mathematica as a giant calculator here, not really as a programming tool, but hopefully it's clear what we're doing here. We calculate the geometry we need here for each one of these steps, and then calculate the 2-electron integral as an accumulating sum within this quadruple loop, looping over a number of primitive Gaussian functions. So the 1, 1, 1, 1 term, the 2, 1, 1, 1 term, calculating the 2, 1, 2, 1 term. So there's 3 of the 6 we need. Let's just slowly go through here so you can see the rest of them. 2, 2, 1, 1 term. And of course I didn't type these equations into Mathematica over and over again. I just copied and pasted and edited them. Very easy. If you see 2, 2, 1, 1, then in the equation it's very clearly 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1. So it's very easy to modify the equations as you need to get these different values. So okay, 2, 2, 1, 1, and 2, 1, 2, 2, 2, 1, and then finally 2, 2, 2, 2, all the values 2 across here. So a lot of copying and pasting to do that, and minor editing of each equation. And then close our quadruple loop that goes from 1 to 3, 1 to 3, 1 to 3, 1 to 3. So then we have these values. We can print them out and look at them, and we should have the same values that Szabo obtains in the appendix. So there they are. There's our 6 values we need. Those should check out if you're following in the textbooks, the same values. And then we're going to do finally what Szabo calls putting them into pretty arrays. We'll go ahead and put this into an array of 16 elements that we can access. It makes it easier later on to access these. We calculated 6, but they're going to fill up a matrix of 16. Don't really have to do that, but it's neat and pretty, as Szabo says. So we'll do that as well. So let's go to there. Here we're going to load them up into a 2-electron matrix called 2, and then we'll create our 16 values from the 6 that we calculated. And again, if you want to prove this to yourself that these work, just write these integrals out in chemist notation and switch dummy variables. Realize we're dealing with real numbers here, and then it should work out for you. So see, let's open up the rest of this. And there you can see there's our 16-member array. Excuse me, our 16-member array all filled up. So they are loaded into pretty arrays, as Szabo says, ready to access later as we need them. So now we're ready for step 3. We'll do that in the next video. Thank you very much for watching, and I'll see you in video 3. Bye-bye.